Please subscribe to support the channel. You're looking at a $10 billion machine that shows you the past, not in theory, but in actual data, one image at a time. The James Webb Space Telescope is not just a better Hubble, it's an infrared observatory parked about 1 million miles from Earth, built for one main purpose: to reveal parts of the universe that are too old, too faint, and too stretched out in wavelength for anything else to see. Here's the core idea. Every time Webb looks farther out into space, it looks further back in time. Light does not get to you instantly, it has to travel. If a galaxy is billions of light years away, the light Webb collects left that galaxy billions of years ago, when the universe was much younger. So distance is time. The farther the target, the earlier the snapshot. But that alone doesn't explain why Webb had to be an infrared telescope. The extra step is redshift. As the universe expands, space stretches, and the light waves moving through that space stretch with it. Light that started out as ultraviolet or visible gets pulled to longer wavelengths into the infrared. So the first generations of galaxies, which shined in normal starlight when they formed, now show up as faint, stretched infrared signals after more than 13 billion years of travel. That's why Webb's main cameras are tuned to infrared. NRCam covers the near infrared from just beyond deep red into several times longer wavelengths. MRCam covers the mid-infrared, even farther out. Together, they cover roughly the band where early universe light has been dragged by cosmic expansion. When you see those tiny reddish blobs in Webb's deep images, you're not just seeing red galaxies, you're seeing extremely distant systems whose light has been stretched by the growth of the universe itself. That's the time machine part. No fantasy, just physics, light, distance, and expansion. So if seeing the earliest galaxies means chasing this stretched out infrared light, why did NASA send Webb so far away from Earth instead of keeping it in a simple, close orbit like Hubble? The reason is straightforward. Infrared is basically heat, and anything warm glows in infrared, including the telescope. If Webb stayed near Earth, it would be constantly hit by heat from the sun, the Earth, and the moon. Its own structure would warm up, and its detectors would be flooded with infrared noise from the telescope itself, swamping the faint signals from distant galaxies. To avoid that, Webb sits near a point in space called the Sun-Earth L2 point, about 1 million miles away from Earth on the night side. At that location, the Sun, Earth, and Moon are all roughly in the same part of Webb's sky, so a single giant sun shield can block them all. That sun shield is about the size of a tennis court, made of 5 thin reflective layers. On the sun-facing side, it gets very hot, but on the other side, where the mirrors and instruments live, the temperature drops to around minus 370 degrees Fahrenheit. That extreme cold is not a bonus, it is mandatory. The detectors must be colder than the objects they are observing, or else the telescope's own heat would drown out the cosmic signal. Webb doesn't sit exactly at L2 like a rock. It orbits around it in a large halo orbit, staying in constant shadow behind the shield, with clear access to deep space. That orbit keeps the thermal environment stable, keeps the sun and Earth always on the same side of the sun shield, and lets Webb observe continuously for long stretches without Earth blocking its view. If the telescope is that far away, that cold, and that protected, the next question is, why did they also make the mirror so huge? And why does everyone keep comparing it to Hubble's? Here's why size matters in a very simple way. A bigger mirror collects more light, and more light means you can see fainter objects. Hubble's mirror is about 8 feet across. Webb's primary mirror is 21.3 feet across, made of 18 hexagonal segments that unfold and align in space to act like one surface. In terms of area, Webb collects over 6 times as much light as Hubble. That extra light gives Webb 2 huge advantages. First, it can detect extremely faint, distant galaxies that Hubble either barely saw or didn't see at all. Second, a larger mirror also improves sharpness, so Webb can separate fine details that would blur together in Hubble's view. When you compare images of the same region, Hubble shows some faint fuzz. Webb breaks that fuzz into many tiny, distinct galaxies, some of them from the first few 100 million years of cosmic history. That's not just nicer pictures, that's a different level of access to the early universe. But collecting light is still only step one. The crucial part is what Webb does with that light. So the question becomes, how does this telescope turn a dim speck of light into hard numbers about distance, motion, temperature, and chemistry? Webb carries four main instruments that split up the work. NIRCam is the main near-infrared camera. It takes deep images through different filters, helping scientists pick out candidate very high redshift galaxies and map structure. NIRSpec is the near-infrared spectrograph. It doesn't just take pictures, it spreads incoming light into spectra, breaking it into wavelengths, like a detailed barcode. From those spectra, astronomers read the fingerprints of atoms and molecules, measure redshift very precisely, and see how fast things are moving away from us. NIRSpec can observe many targets at once, using tiny adjustable shutters, so in one pointing it can gather spectra for dozens or even hundreds of galaxies. MIRI handles mid-infrared imaging and spectroscopy. It sees cooler objects and dust structures and light that's been stretched even more. It is great for dust-rich galaxies, star-forming regions, and certain molecules that glow in mid-infrared bands. Then there is FGS/NIRIS, a combination of a fine guidance sensor and an extra science instrument. The guidance sensor keeps Webb locked on its targets with extreme stability, which is crucial for long exposures and exoplanet observations. NIRIS adds special modes, for example, techniques used to study exoplanet atmospheres and high-contrast imaging near bright stars. The key point here, the real science bombs usually come from spectra, not just images. Pictures tell you what's there and roughly how bright it is. Spectra tell you what it's made of, how old its stars likely are, how much dust it contains, and exactly how far back in time you're looking. Webb was built to gather those spectra in bulk, across the deep universe and in local targets, so it doesn't just show you the universe, it interrogates it. With that level of hardware and complexity, why did NASA and its partners take such a huge risk on this one telescope? What were the main promises that had to be strong enough to justify $10 billion and a one-shot launch? From the start, Webb was pitched with two headline goals. First, see the first generations of galaxies, the ones forming only a few 100 million years after the Big Bang, and turn them from theory into data. Second, study the atmospheres of planets around other stars in real detail. Not just detect that an atmosphere exists, but measure its gases and chemistry. First light and first atmospheres. That was the bargain. If Webb could do those two things, it would change both cosmology and exoplanet science. What nobody fully expected was how quickly it would start pushing beyond those promises, finding galaxies that are brighter and more massive than our models predicted so early on, and reading exoplanet atmospheres with a clarity that has already forced scientists to update their models. So now the real tension starts. When Webb stares at a patch of sky that looks empty to your eyes, what does it actually uncover there? And why did one of its very first deep images immediately make cosmologists uncomfortable about our standard picture of the early universe? How crowded do you think the universe is when a piece of sky smaller than a grain of sand held at arm's length is stuffed with thousands of galaxies, some from when the universe was under 5% of its current age? That's what Webb's first deep field is about, the SMACS 0723 galaxy cluster. The actual area on the sky is tiny, only a couple of arc minutes across, but when Webb stared at it for about 12.5 hours with NIRCam, the result was a frame packed with galaxies. Big ones, tiny ones, stretched arcs, faint dots, all layered on top of each other in distance and time. At the center of this field sits the cluster SMACS 0723.3-7327, about 4 to 4.6 billion light-years away. So what exactly is this cluster doing for you? It's not just sitting there, it's acting like a lens. The combined mass of all its galaxies plus the dark matter around them warps spacetime strongly enough that light from background galaxies doesn't travel in straight lines. It bends around the cluster, just like light refracting through glass. And that bending magnifies and stretches the more distant galaxies behind it. This is gravitational lensing. Instead of seeing those background galaxies as neat circles, you get arcs, smeared streaks, and multiple images of the same object at different positions. That lensing effect is crucial because it boosts the brightness of galaxies that would otherwise be way too faint for even Webb to catch. So here's your first pressure point on our picture of the early universe. What happens when you grab a magnifying cluster, point the most powerful infrared telescope ever built at it, and ask, how far back can I see? In SMACS 0723, Webb didn't just produce a pretty image, it immediately followed up with spectroscopy using its instruments. When astronomers pulled spectra from some of the lensed background galaxies, they measured redshifts that say, very clearly, this light left over 13.1 billion years ago, roughly 600 million years after the Big Bang. That's the universe in extreme childhood. Redshift here is doing the heavy lifting. You see sharp emission lines in the spectrum, caused by specific atoms like hydrogen or oxygen, and you know their home wavelengths from lab measurements. In the SMACS 0723 background galaxies, those lines are shifted way towards longer wavelengths. The amount of shift tells you how much the universe has expanded while the light was traveling, and that links directly to how long the light has been in flight. When Webb's spectra say 13 plus billion years of look-back time, you are not debating maybe early, maybe not. You are pinned deep into the first 5% of cosmic history. But the really uncomfortable part starts when you count how many distant galaxies show up and how bright they are. The expectation before Webb was that very early galaxies would mostly be small, faint, and rare in such a tiny field. Instead, studies of the SMACS 0723 deep data report a surprising number of bright, compact, high redshift candidates. Even with all the uncertainties and lensing corrections, you still end up with an early universe that looks busier and more mature than many simulations predicted. So ask yourself this. If in one tiny patch of sky you already seem to have too many big, bright galaxies too early, what happens when you survey dozens of fields like this? Either galaxy formation is more efficient than we thought, or our assumptions about how light maps onto mass or how fast dark matter halos assemble are off. SMACS 0723 was one of the first hints of this galaxy overload problem, and it showed up right out of the gate in the very first deep field Webb released. Images alone would not be enough to make that case. You need hard numbers, and that means spectra. So how does Webb actually rip those detailed fingerprints out of such a crowded scene without wasting time on one galaxy at a time? Here's where NIR-SPEC's microshutter array comes in. Behind the scenes, NIR-SPEC has a grid of about 250,000 tiny shutters that can open and close independently. Astronomers can program a pattern so that tens or even around 100 shutters line up with specific galaxies in the field. During one exposure, NIR-SPEC spreads the light from each of those targets into its own spectrum. That means one pointing can give you distances, velocities, and chemical information for a whole sample of galaxies at once instead of just one. Those spectra do more than confirm this object is far away. They show you the presence of elements heavier than helium, what astronomers call metals in this context, things like oxygen, nitrogen, neon. When you see clear metal lines at such high redshift, it tells you that several generations of stars have already lived, produced those elements through nuclear fusion and supernova explosions, and spread them back into the gas. In other words, by the time you are only a few 100 million years after the Big Bang, star formation has already been running long enough and hard enough to enrich galaxies with heavy elements. That's a very fast start. And there's one specific background galaxy in SMACS 0723 that adds an extra layer of tension, the so-called sparkler galaxy. In the deep field data, this object appears as a lensed, compact galaxy decorated with multiple tiny point-like clumps, like bright specks surrounding it. Some of those spots look a lot like what we see in nearby galaxies as old globular clusters, dense balls of hundreds of thousands of stars. Here's the problem. If those clumps really are ancient globular clusters, then you're seeing star clusters that formed only a few 100 million years after the Big Bang, already long-lived, already tightly bound, orbiting a young galaxy. That pushes the formation of some of the universe's most stable old stellar systems to times much earlier than many models assumed. Globular clusters in our own galaxy are some of the oldest structures we know. Moving that whole timeline earlier forces theorists to rethink how quickly dense star clusters can assemble and survive. So step back for a second and stack all of this together. In a tiny patch of sky, one cluster lens reveals a background forest of galaxies, some from 13.1 billion years ago, more bright systems than expected that early, heavy elements already present, and possibly ancient star clusters forming on ultra-fast schedules. None of these individually kill our standard cosmology, but together they say loudly your default settings for how fast structure builds up might be wrong. And that leads straight to the next, sharper question. If the very first deep field already shows the universe looking too busy, too enriched, too structured, what happens when Webb stops sampling lensed fields and starts locking onto galaxies even earlier than this, at redshifts 13, 14, and beyond, where you are only 300 million years after the Big Bang? How close to the Big Bang can you really go before galaxies should not exist yet? And why is Webb already finding bright systems only a few 100 million years after everything started? This is where MOMZ14 and its friends come in, the current record holders for earliest confirmed galaxies. Right now, the champion is MOMZ14, a small but extremely bright galaxy whose light started its trip only about 280 million years after the Big Bang, at a redshift of about 14.4. That makes it the most distant confirmed galaxy known so far. Webb picked it out with NIRCam and then used NIRSpec to get a spectrum with a sharp break and several emission lines, which lock in the redshift and age. 280 million years after the Big Bang is early. Before Webb, most models expected small, dim systems here, if anything. Instead, MOMZ14 is already a luminous galaxy with a mass of around 100 million suns, similar to a small satellite galaxy packed into a region only a few hundred light years across. It is forming stars so intensely that its ultraviolet light, stretched into the infrared by expansion, still stands out clearly. So the question becomes direct. How does a universe that young already build a galaxy that bright? The spectrum shows strong ultraviolet emission lines and very little dust, which means you're catching a burst of recent star formation in a compact system dominated by massive hot stars. And it's not alone. Early Webb surveys suggest that galaxies this bright at such high redshift are far more common than expected, tens to hundreds times more frequent than pre-Webb models predicted. That's why the Discovery team calls it a cosmic miracle. If MOMZ14 is the current mother of all early galaxies, it sits in a growing family. Slightly later in time, around 330 million years after the Big Bang, you have another key object, JADE's GS Z13-1. This galaxy comes from the JADE's Deep Survey, where Webb stared for tens of hours and then used NIRSpec to get spectra from faint red candidates. For JADE's GS Z13-1, the spectrum gives a redshift of about 13.0, translating to light that has been traveling for roughly 13.5 billion years. JADE's GS Z13-1 is not a fragile first flicker. It shows a strong Lyman alpha emission line from hydrogen, which should have been heavily blocked by the neutral hydrogen fog filling space at that time. Yet the line comes through clearly. The simplest reading is that the small, early galaxy has already carved out an ionized bubble around itself, clearing a path for that light to escape. You are dealing with a system only a few hundred light-years wide, already running intense star formation and punching a hole in the cosmic fog. So put MOM Z14 and JADE's GS Z13-1 side by side. One sits at about 280 million years, one at about 330 million years after the Big Bang. That already pushes back against the idea that early structure should grow slowly, from tiny, quiet seeds. The next step is to ask, what do these systems tell you about star formation and chemical enrichment in that era? Here, the 13.4 billion-year-old starburst galaxy comes in. In this case, astronomers used Webb plus ALMA, the big radio array in Chile, to study a galaxy seen when its light had been traveling for about 13.4 billion years. The data show an extreme burst of star formation in a compact region. Even at this early time, the gas already has a metallicity, a heavy element fraction, of about 10% of the Sun's, meaning many stars have already formed, lived, and exploded, spreading oxygen, carbon, and other elements into the gas. That is another warning signal for the simple picture of first galaxies equals almost pure hydrogen and helium. Instead, you are seeing systems that already look chemically evolved, with multiple cycles of star birth and death compressed into a few 100 million years. In a slow growth model, it takes longer to reach that level of metal enrichment and star formation. Webb and ALMA are telling you that enrichment and starburst activity ramped up very fast. Once you accept that these galaxies exist and that they are this bright and this enriched, you hit the main tension point. How do you build that much stellar mass and that much luminosity in such a short time? In standard simulations, dark matter halos grow gradually, gas falls in, cools, and forms stars with a moderate efficiency tuned to match galaxies in the later universe. When you run those recipes at very early times, you usually do not get many big, bright galaxies at redshifts above 10. To line up theory with data, something in that chain has to change. One option, dark matter halos at early times assemble faster and reach higher masses sooner than standard models assumed. Another, gas in those halos cools more quickly and collapses more efficiently. A third lever is star formation efficiency itself, the fraction of gas that turns into stars. And then there is the stellar initial mass function, the distribution of stellar masses at birth. If the early universe preferred to make more massive, short-lived stars than we see locally, you get a lot of ultraviolet light and metal production from a relatively modest amount of stellar mass. So the real question for you is this. Are Malm Z14, Jade's GS Z13-1, and the 13.4 billion-year-old starburst galaxy rare outliers, or are they sampling a common, extreme mode of early galaxy formation that our simulations simply missed? As Webb keeps stacking deep exposures and confirming more objects at redshifts 10, 12, 14, and beyond, the evidence is shifting toward a universe where the first galaxies form fast, shine hard, and enrich their surroundings quickly. And if this is the level of activity you already see by 300 million years after the Big Bang, that sets up the next step. You have bright galaxies, intense star formation, and strong radiation fields. The obvious question is, how does all of that interact with the thick hydrogen fog that still fills space at this time? And can Webb actually catch the moment when that fog begins to lift and the universe turns transparent? The early universe was not a clean, transparent void. It was full of light that couldn't get very far because space itself was packed with neutral hydrogen that blocked it. The basic problem is simple. After the Big Bang cooled enough, protons and electrons combined into neutral atoms, and that neutral hydrogen is very good at soaking up high-energy ultraviolet light. Until enough stars and galaxies switch on and start blasting that hydrogen apart, the universe in ultraviolet is basically fogged out. Light sources exist, but their radiation cannot travel freely through space. That stretch of time is what cosmologists call the cosmic dark ages, and the moment that fog lifts is the epoch of reionization, when hydrogen gets ionized again and space turns transparent to UV. So here's the key question. How do you actually catch that switch in real data? Not just theory. How do you see the fog turning into clear air? Neutral hydrogen is especially good at blocking one specific type of light, called Lyman alpha. That's a particular wavelength of ultraviolet light emitted when electrons and hydrogen atoms jump between energy levels. In a universe full of neutral hydrogen, Lyman alpha photons scatter over and over and basically get trapped. They don't travel cleanly to us, they bounce around and vanish into the fog. Only once regions of hydrogen get ionized, turned into free protons and electrons, can Lyman alpha radiation escape from galaxies and make it across cosmic distances. So, detecting strong Lyman alpha from very early galaxies is like seeing a hole in the fog, a bubble of cleared ionized gas around them. That leads straight to the new Webb result, because astronomers have now seen a galaxy at redshift 13 throwing out a surprisingly bright Lyman alpha signal, when the universe is only about 320 to 330 million years old. Under old expectations, that line should be heavily suppressed at such an early time, because the hydrogen between galaxies should still be mostly neutral and opaque to that light. Instead, Webb spectroscopy shows a clear, strong Lyman alpha line from a Z equals 13 galaxy, with a strength level usually only seen much later, when the universe is mostly reionized. If that line is getting out, it means the galaxy is not sitting in a uniform fog. It has already carved out a local bubble of ionized hydrogen around itself, a pocket of transparent space in an otherwise hazy universe. That bubble is not tiny. Modeling of the data suggests a region hundreds of thousands of light years across, where hydrogen is ionized enough to let UV light escape. For such a young galaxy to build that bubble, it has to be pumping out a huge amount of ionizing ultraviolet radiation in a relatively short time. That is your first direct sign that reionization is not just underway by redshift 13, it is already locally advanced around some early galaxies. So, which galaxy is doing this, and why is it so efficient at clearing its surroundings? The most discussed case right now is JADE's GS-Z13-1, one of the galaxies found in the JADE's Deep Survey. Webb sees it as it was around 330 million years after the Big Bang, at a redshift of about 13. It's compact, roughly a couple hundred light years across, much smaller than the Milky Way, but incredibly intense in star formation. When astronomers looked at its spectrum with JWST, they saw a bright Lyman alpha line, far stronger and clearer than expected for such an early time. Follow-up analysis suggests this galaxy has already created an ionized bubble in the surrounding intergalactic medium, with a radius on the order of hundreds of thousands of light years across, and possibly up to about 650,000 light years across. That is a serious clearing job for a tiny system in a young universe. To ionize that much gas, JADE's GS-Z13-1 must host either a very intense burst of massive, hot stars or an additional power source like an actively feeding black hole, or both. Some models suggest stars up to a few hundred times the mass of the Sun could be contributing, blasting out ultraviolet photons that rip electrons off hydrogen atoms and keep the gas ionized. The important point is that this galaxy is doing in a couple hundred million years what older models thought should take longer and require larger, more evolved systems. The fog is not just slowly thinning everywhere at once, it is getting punched through by aggressive early galaxies that clear big holes around themselves. If an individual galaxy at 330 million years can already blow that kind of bubble, the next question is obvious. What does that mean for the overall timeline of reionization, and how fast did the universe go from foggy to mostly transparent? Before Webb, measurements using older telescopes suggested that reionization was mostly complete by about 1 billion years after the Big Bang, corresponding to redshift around 6. Quasar spectra and cosmic microwave background data supported the idea that hydrogen was neutral before that, then gradually got ionized, with the main phase stretching somewhere between redshift 6 and maybe 10. Webb's early galaxy counts and these new Lyman alpha detections now push that picture toward a faster, earlier process. Here's why. Webb sees a surprisingly large population of bright UV-luminous galaxies at redshifts above 10, even up to 13 and 14. Those galaxies are exactly the kind of sources that should produce huge numbers of ionizing photons. Combine that with direct evidence of big ionized bubbles around systems like Jade's GSZ13-1, and you get a scenario where significant chunks of the universe are already reionized by redshift 10 or even earlier, just a few 100 million years after the Big Bang. Recent studies using JWST data argue that the onset of reionization likely began earlier than many older models predicted, with the process well underway by 500 million years and largely complete by around a billion years. So the timeline is getting squeezed. The dark ages do not drag on. They end quickly once early galaxies get going, and that tightening timeline feeds directly back into the question of how extreme those galaxies must be. To clear the universe this fast, early galaxies have to be overachievers. They need to turn a larger fraction of their gas into stars than typical galaxies do today, and they need those stars to be very hot and very bright in ultraviolet. That points toward high star formation efficiency and possibly a top-heavy stellar initial mass function, where more of the stars being born are massive, short-lived monsters that pour out radiation and then explode. On top of that, a significant fraction of their ionizing photons has to escape the galaxy instead of being trapped by internal gas and dust, what astronomers call a high escape fraction. All of this lines up with the pattern Webb keeps showing. Early galaxies are compact, bright, and chemically active far sooner than older models expected. So put the pieces together. You have galaxies only a few 100 million years after the Big Bang carving enormous bubbles in a neutral hydrogen fog. You have the overall reionization process starting earlier and finishing faster than many models assumed. And you have to crank up star formation and radiation output in those systems to make the numbers work. The recurring message is that the early universe is not just a scaled-down version of the later one. It's operating in a more aggressive mode. And if galaxies are already that intense, that efficient, and that disruptive while the fog is still lifting, then the next step is almost unavoidable. You should start seeing entire galaxies that just don't fit standard expectations at all. Too big, too bright, too massive for their age, forcing you to ask whether the basic recipes in your simulations are missing something important. How wrong does your rulebook have to be if galaxies that are supposed to be tiny and barely formed are already big, bright, and complicated just a few 100 million years after the Big Bang? That's the situation Webb has forced you into. It's not just that galaxies show up early, it's that everything about them, their number, their brightness, their shapes, their internal physics, looks off compared to what standard models said you should see. Start with the simplest problem, the head count. In a universe only about 300 to 500 million years old, simulations based on the standard LCDM cosmology predicted mainly small, faint galaxies, slowly building up mass. Instead, Webb deep surveys like Jade's, Sears, and others keep finding a remarkable array of bright galaxies at redshifts above 10, and a strong excess of luminous systems at redshifts 7 to 10. When theorists plug those observed numbers into the standard framework, they run into a limit. The most massive candidates at those redshifts sit right at or even beyond what lambda CDM would comfortably allow, if you assume conventional star formation and mass-to-light ratios. One high-profile analysis, literally titled Stress Testing Lambda CDM, showed that some of these galaxies pushed the model to its edge. Now, over the last couple of years, better data and more careful modeling have trimmed back some of the early monster galaxy claims, so it's not that every object breaks physics. But even with more conservative mass estimates, you still end up with more bright galaxies earlier than expected. In plain terms, the early universe is busier and more lit up than the textbook said. So if the number and brightness are too high, what does that actually mean physically? What has to be different inside those galaxies? Brightness in the ultraviolet and infrared is tied to how many young massive stars you have and how fast you are forming them. For a given amount of dark matter and gas, you can only ramp that up in a few ways. You either turn gas into stars more efficiently than local galaxies do, or you change the kind of stars you make. Many recent studies use Webb data to probe this by tweaking the star formation efficiency and the stellar initial mass function in their models, and seeing what it takes to reproduce the observed luminosity functions at high redshift. In simple language, star formation efficiency is out of the gas available, how much ends up as stars. Locally, that fraction is modest, and it takes billions of years to build a big galaxy. Webb is pushing you toward a picture where early galaxies, at least the ones you see, might be turning gas into stars much more aggressively on short timescales. Then there's the idea of a top-heavy initial mass function. Normally, when stars form, most of them are low-mass, long-lived stars, and only a minority are big, hot, short-lived ones. But several theoretical and observational works now suggest that in the low metallicity, high-pressure conditions of the early universe, the distribution might shift. More massive stars per unit of mass of gas, fewer small ones. If that's true, you get a double effect. Massive stars are insanely bright in UV, so your galaxies look more luminous for the same mass. And they live fast and die young, dumping heavy elements into the gas quickly. That makes it easier to explain why some early galaxies already show significant metal enrichment. But it also means our usual way of converting light we see into mass of stars can be off, because it assumes a more normal mix of star masses. So already, just from brightness, Webb is pushing you to consider early galaxies that are more efficient, more extreme, and possibly populated by a different kind of stellar population than what you see in the nearby universe. The story gets stranger when you look at shapes. If you picture galaxies, you probably think of nice spirals or smooth elliptical blobs. Webb's deep fields at high redshift do not look like that. Instead, you see chains of elongated clumps, distorted structures, and tiny red dots with strange internal behavior. Some galaxies appear as chain galaxies, strings of bright knots that may be multiple star-forming regions merging along filaments of gas. Others break into several clumps that look like they are in the middle of collapsing together. And then there are the little red dots, compact, very red, distant objects that only Webb could pick up. At first glance, they look like simple, tiny blobs, but when astronomers study them at different wavelengths, a fraction of them reveal clumpy, disturbed structures in the ultraviolet, suggesting complex internal dynamics and possibly buried black holes. The key point for you: these early galaxies do not resemble the stable disks and big ellipticals you see nearby. They look like proto-galactic fragments colliding and merging in real time, with gas flows, starbursts, and maybe rapidly growing black holes all happening at once. This matches the general idea that structure builds up hierarchically, but the intensity and the organization of those clumps in some systems still push beyond what many simulations predicted at such early times. So what do theorists do when the data start pulling away from their models? Do they throw out the whole cosmological framework, or do they start turning knobs inside the galaxy formation recipe? Right now, the main effort is in the second category, trying astrophysical fixes before declaring new physics. Several directions are on the table. One is that gas flows into early halos faster and more continuously than simple models assumed, feeding starbursts. Another is that gas cools more efficiently, letting galaxies condense and ignite stars earlier. Feedback from stars and black holes, which in later galaxies often shut star formation down, might behave differently at these early times, maybe clearing just enough dust to let UV out while not yet blowing all the gas away. There's also a lot of work revisiting how we infer masses and star formation rates from the light Webb sees. Nebular emission lines and hot dust can boost certain infrared bands, making galaxies look more massive if you misinterpret those contributions. Updated models that carefully include those effects can pull some early too massive galaxies back into a safer range, though not all of them. On the more radical side, some papers test tweaks to the small-scale behavior of dark matter or to how halos collapse at early times, trying warmer dark matter, modified power spectra, or other changes. Others even ask whether gravity itself might behave differently on certain scales. Though so far, the standard lambda CDM model has held up better than the early hype about cosmology is dead suggested. So you're in an interesting place. The core cosmological model is not demolished, but the details of how galaxies form, light up, and grow in the first few 100 million years are clearly not solved. The early universe that Webb is revealing is noisy, clumpy, and surprisingly luminous, and your old recipes are being edited in real time. That's the real message you should take from this beautiful confusion. These galaxies are not just a footnote or a minor adjustment. They are a direct challenge to the standard pipeline that turns dark matter into starlight in simulations. The standard picture of galaxy formation is now more like a working draft, with whole chapters on early star formation, feedback, and stellar populations under heavy revision. And if the galaxies themselves are already this extreme, that naturally raises the next question. What is going on inside them at the level of individual stars and black holes? Are these systems being powered by a completely different breed of stars? Huge, short-lived giants that dump energy and collapse into black holes fast enough to seed the supermassive monsters we see later? To answer that, you have to zoom in to specific galaxies and read their chemical fingerprints, and Webb has already delivered one of the most dramatic clues so far: hints of monster stars and baby black holes in the early universe. How extreme do stars have to be if the chemistry of an early galaxy cannot be explained by any kind of normal star we know today, and the only answer left is we need a whole new class of monster stars? That is what Webb has just done with the galaxy GS3073. Webb's spectroscopy shows this system about 12.7 billion light-years away, as it was roughly 1.1 billion years after the Big Bang. When astronomers pulled out about dozens of emission lines from its spectrum and measured the abundances, one number jumped out: the nitrogen to oxygen ratio, around 0.46. That is orders of magnitude higher than the typical value in local galaxies at similar metallicities. In simple terms, there is way too much nitrogen in this galaxy. Normal populations of massive stars, even exotic ones like Wolf-Rayet stars, cannot get you to that ratio without breaking other constraints. Chemicals in a galaxy act like a fingerprint. Oxygen mostly comes from ordinary massive stars exploding as supernovae. Nitrogen is trickier. It can be produced in intermediate mass stars over long times, or in special conditions in very massive stars. When you see nitrogen this high without a matching crazy excess in other elements, it tells you something very specific about the stars that polluted that gas. Teams working on GS3073 tried every standard option. They tested mixes of normal massive stars, extreme starbursts, even combinations involving active black holes. Nothing matched the pattern of nitrogen, oxygen, carbon, and neon all at once. So the next step was blunt. What kind of star would you need to generate this kind of nitrogen fingerprint? That is where the monster star idea finally moved from theory into data. Researchers use stellar evolution models for primordial stars with masses between about 1,000 and 10,000 times the mass of the Sun. These are far beyond any star you see today. In the models, these giants burn helium in their cores and create carbon. Some of that carbon leaks into an outer shell where hydrogen is burning. There, carbon and hydrogen fuse to make nitrogen, and convection carries that nitrogen out through the star. Over a few million years of burning, the star can dump huge amounts of nitrogen into its surroundings through winds. When those yields are compared to the weird chemistry of GS3073, the match is striking, especially for stars in the 1,000 to 10,000 solar mass range. That is why these things are being called monster stars or dinosaur-like stars. They are massive, short-lived, and gone now, but their chemical fossils remain in the gas of galaxies like GS3073. Models suggest they live only about 250,000 years, a quarter of a million years, before they reach the end of their lives. That's an instant on cosmic timescales. Here is the crucial part. They probably don't explode as normal supernovae. For such extreme masses, the simulations say the core collapses directly into a black hole without a big explosion that would blow everything apart. You go from a star that's thousands of solar masses straight to a black hole that's also thousands of solar masses. No long growth phase, no slow buildup from many small stars. That gives you seed black holes already in the intermediate mass region from day one. Now connect that to another big puzzle. How do you get supermassive black holes, millions or billions of solar masses, already in place less than a billion years after the Big Bang? Webb and other observatories have found quasars and active galaxies in that era, with central black holes of 10 million, 100 million, and even close to a billion solar masses. Under standard growth from normal mass black hole seeds, that's hard to do in time. Monster stars provide a shortcut. If GS3073 hosts several of these giants early on, each collapsing directly into a black hole of a few thousand solar masses, then those black holes can merge and accrete gas. Very quickly, you're not starting at 10 or 50 solar masses, you're starting at thousands. That's a huge head start. In GS3073, Webb data already show an actively feeding central black hole, which fits the idea that you're seeing the descendant of one or more of these monster stars now sitting in the nucleus and growing. Once those seed black holes start feeding, they're not passive. As gas spirals in, they launch radiation and sometimes jets that push back on the galaxy. That feedback heats and stirs the gas, and it can do two opposite things. It can blow gas out of the center or heat it enough to shut down star formation locally. Or it can compress pockets of gas elsewhere and trigger new bursts of star formation. Over long times, this kind of feedback is what seems to lock galaxies and their central black holes into tight relationships, like the observed link between black hole mass and the random speeds of stars in a galaxy's bulge, the so-called M-sigma relation. Webb is now starting to show you that this galaxy-black hole connection might start much earlier than we thought, with heavy seeds already in place in compact young galaxies. So, step back and look at what GS3073 and this nitrogen puzzle are really telling you. To explain one galaxy's chemical fingerprint, you're forced to accept a class of stars that aren't just bigger versions of familiar ones. They are operating in a regime where their internal structure, their fusion paths, and their deaths are all different. They enrich their environment in a unique way, and they leave behind black holes that skip several growth steps. That's not a small tweak to stellar astrophysics, it's a major extension. The bigger message is the first generation of stars, the so-called population 3 stars, might not just have been slightly more massive or slightly hotter than today's stars. They could have included truly supermassive objects, thousands of solar masses that lit up early galaxies, rewrote their chemistry, and laid down the first heavy black hole seeds. Webb isn't seeing those stars directly, but it's reading their fingerprints in the gas, and those fingerprints don't match anything else we know. So now you have an early universe where galaxies form faster than expected, where some stars are far more massive than any we see today, and where seed black holes can start out already huge. The next logical question is, if black holes can grow that fast and move that much gas around, what happens when one of them gets kicked out of its own galaxy at unbelievable speed and starts plowing through space, reshaping gas and triggering star formation far from any normal galactic center? How strong does a kick have to be if it can throw a black hole 10 million times the mass of the sun out of its own galaxy and send it tearing through space at more than 2 million miles per hour? That's not a thought experiment anymore. It's a measured object. Using Webb, astronomers have now confirmed the first runaway supermassive black hole, racing through a pair of interacting galaxies nicknamed the Cosmic Owl, about 8 to 9 billion light-years away. This thing weighs roughly 10 million suns, and it's no longer sitting calmly in the galactic center, it's charging through the outer regions, heading for intergalactic space. The cosmic owl itself is already a wild system. Two ring galaxies in the middle of a merger, with active galactic nuclei and intense star formation where their gas is colliding. Webb, ALMA, and radio data together have mapped out the structure, the twin rings, the shock fronts, the gas being stirred up. In that chaos, earlier Hubble images showed a long, thin streak of light, about 200,000 light-years long, pointing away from the galaxy pair. It looked like a wake, but no one could prove what was driving it. Webb's job was to go in with sharper infrared eyes and hard spectroscopy and settle the question. So what did Webb actually measure that turned a weird streak into a confirmed runaway black hole? When astronomers pointed Webb's NIR spec at the tip of that streak, at the point closest to the cosmic owl's core, they saw something very specific in the gas. The spectrum showed a strong gradient in line-of-sight velocity, and emission line profiles shaped exactly like you expect from a bow shock, gas being slammed and heated by something moving supersonically through it. The Doppler shifts in those lines say the gas at the front is moving at about 1,000 kilometers per second, which is roughly 2.2 million miles per hour. That's not a random flow. That's consistent with a massive object bulldozing through the gas and dragging material along with it. To be clear on the speed, 2.2 million miles per hour is way beyond typical stellar motions in a galaxy. At that pace, you could cross the Earth-Moon distance in under 7 minutes. It's also fast enough to fully escape the gravity of the host galaxy. And the object producing the shock is not a star cluster or a small black hole. Modeling of the wake and energy budget points to a supermassive black hole of around 10 million solar masses plowing through the gas. That's why this is a big deal. It's not just a fast object, it's a supermassive black hole that has been physically kicked out of the galactic center. Now look along the full length of the streak. Webb's data show this is not just hot gas being dragged along. The tail is packed with new stars forming. The structure stretches roughly 200,000 light-years from the galaxy toward the direction of motion. At the front, gas is compressed into a bow shock. Behind that, the pressure drops, gas piles up and cools, and pockets of it collapse into star-forming regions. You end up with a line of starbirth in what would otherwise be relatively empty intergalactic space. This is star formation driven by a runaway black hole, not by a normal galactic disk or spiral arm. So you have the basic picture. A 10 million solar mass black hole ripped out of its original central home, now burning across the outskirts of a merging galaxy pair at over 2 million miles per hour, with a galaxy-scale shock front in front of it and a 200,000 light-year trail of newborn stars behind it. The important thing for you is that this is not some isolated freak that doesn't matter for the bigger story. It's direct evidence that black holes don't just sit in the middle of galaxies quietly shaping them from the center. They can be thrown out and still keep rearranging gas and triggering star formation on their way out. The runaway black hole in the cosmic owl is effectively drawing a new mini-galaxy behind it, a linear sequence of stars that did not come from a standard rotating disk, but from shocked gas in its path. That's a completely different mode of building structure. It also tells you something about feedback. We usually talk about black hole feedback as radiation and jets from the central engine heating the gas, turning off star formation, or regulating it in the host galaxy. Here, feedback is happening off-center, along a path through the halo and into intergalactic space. Gas that might have stayed diffuse is being compressed and turned into stars because a black hole is racing through it. That means some fraction of stars and stellar mass in the universe may have been formed in environments like this, far from neat galactic disks, shaped by violent black hole dynamics. So now link this back to the early universe story. Webb is showing you that supermassive black holes existed very early, that some may have formed from monster stars, and that mergers can kick them out of galaxies and make them active sculptors of gas even on the run. The runaway black hole in the cosmic owl is a nearby, high-resolution example of something that could have been happening all over the early universe, when mergers were more common, gas was denser, and black holes were growing fast. If a single black hole can leave a 200,000 light-year trail of star formation when it gets thrown out, then imagine what happens in a region where gas is already thick and turbulent, and stars are forming everywhere, even without a runaway object plowing through. That's exactly what Webb shows you next, not in some distant, barely resolved dot, but in our own galaxy, where it can zoom in on a wall of gas and catch dozens of newborn stars and jets in action. The question now is, if a rogue black hole can paint a line of stars across intergalactic space, what does star birth look like in a normal but extreme nursery much closer to home, where Webb can resolve every jet, shock, and collapsing clump in brutal detail? How extreme is star birth really if one small patch of our own galaxy is already full of collapsing clouds, newborn stars, and supersonic jets punching holes in gas? That's what Webb's cosmic cliffs are showing you. This region, NGC 3324 in the Carina Nebula, sits roughly 7,600 light-years away in the southern sky. It's the edge of a huge hollowed-out cavity inside the nebula, carved over time by radiation and winds from massive hot stars sitting just above the area Webb imaged. The ridge you've seen labeled as the cliffs is not small. The tallest structures there are around 7 light-years high, which is about 41 trillion miles. You're looking at a wall of gas and dust on the scale of an entire star system, packed with places where new stars are forming right now. Here's the key point. Hubble already looked at Carina and it saw beautiful gas structures, but it missed a lot of what matters most, because visible light can't get through thick dust. Webb, using infrared light, can. NIRCam and MIRI pick up longer wavelengths that slip between dust grains instead of getting blocked. Suddenly, regions that were just dark lanes in Hubble's view fill up with point sources and fine structure. You're not guessing where stars might be hiding anymore. You see them directly. In the cosmic cliffs, Webb reveals emerging stellar nurseries and individual newborn stars that were completely invisible before. Many of these young stars are only a few 100,000 years old, still wrapped in the gas and dust they formed from. Their own light, plus the infrared glow from their warm dust disks, now shows up clearly in Webb's data. This is exactly the phase where stars like the Sun gain most of their mass, and where planets start to assemble in disks. And until now, a lot of that process was buried behind opaque dust. So once you can see through the dust, the next question is, what are these newborn stars actually doing to their surroundings? How calm or violent is this process? When scientists took a deeper look at the cosmic cliffs with NIRCam using narrowband filters, they isolated light from specific molecules, especially molecular hydrogen. That's a crucial ingredient for star formation, and it also lights up in shocks where fast-moving gas slams into slower material. In those narrowband images, dozens of jets and outflows suddenly jump out. These are straight, collimated streams of gas shot out from the poles of young stars that are still pulling in material from their disks. Webb's data reveal many jets that were completely hidden in previous images, including at least 24 newly identified molecular outflows and multiple Herbig-Haro objects traced in hydrogen emission. Those jets are not gentle. They travel at hundreds of thousands of miles per hour, plowing into the surrounding cloud, heating it, and carving narrow channels through the gas. In the Webb images, they show up as thin streaks, knots, and bow-shaped shocks. By mapping them, astronomers can track exactly where young stars are hiding, even if the stars themselves are still deeply buried. They can also tell which direction material is flowing and how much energy these baby stars are dumping back into their environment. So, star birth in NGC 3324 is not just gas quietly collapsing. It's gas collapsing, stars switching on, and then those stars immediately firing jets that punch out cavities and stir everything up. That raises the next question: who's really in charge of this region? The gravity pulling gas together, or the radiation and winds trying to blow it apart? The big, hot O-type stars that carved the main cavity sit above the ridge Webb imaged. Their ultraviolet light and fast stellar winds have been blasting this region for millions of years. That radiation strips electrons off gas, heats it, and pushes on it. Over time, it has hollowed out the cavity, sweeping material into the dense wall you see as the cosmic cliffs. Inside the wall, local gravity is trying to do the opposite. In denser clumps, gravity pulls gas inward. If the clump can stay dense and cool long enough, it collapses into a new star or a small group of stars. But whether that happens depends on the balance. If radiation and winds are too strong, they disperse the clump before it can collapse. If they are just right, they can actually compress a region and trigger star formation. Webb's view of NGC 3324 shows both outcomes. Some pillars and knots look like they are being stripped away, with gas streaming off their surfaces. Others show signs of ongoing collapse and embedded protostars at their tips, with jets already emerging. So for each potential star, there's a real tug-of-war. Gravity tries to hold the gas together and form a star. Feedback from nearby massive stars tries to rip it apart or reshape it. The final result, how many stars form, what masses they have, and where they end up, comes from that fight. Because Webb can resolve structures down to a few hundred astronomical units in this region, it lets astronomers measure that battle at very small scales in individual filaments and cores, not just averaged over a whole nebula. That brings you to the bigger picture. Why does this local scene matter for the early universe story you've been following? NGC 3324 is not some special alien environment. It's a fairly normal massive star-forming region, larger than Orion, but smaller than the most extreme starburst clusters. The same basic physics you see here, collapse, jets, radiation, winds, erosion, compression, are the tools galaxies had to work with 13 billion years ago too. In early galaxies, you just scale up the density, the number of massive stars, and the violence, and you add in lower metallicity gas. What Webb is doing in Carina is giving you a training set. You watch how O-type stars eat away at gas walls, how jets punch channels, how feedback changes the rate and efficiency of star formation, and then you apply those lessons when you interpret resolved blobs of light in the high redshift universe. So, when you hear that early galaxies seem to be forming stars too fast or clearing the reionization fog too early, this is the kind of small-scale physics that feeds into those big questions. If feedback can sometimes trigger extra star formation rather than just shutting it down, or if dense gas structures can survive longer in intense radiation fields than simple models assumed, that changes how quickly galaxies can grow. Webb's close-up of the cosmic cliffs is not just a pretty milestone, it's a calibration tool for the entire story of how gas turns into stars across cosmic time. And if a single wall of gas in our own galaxy is already this chaotic, with dozens of hidden jets, eroding ridges, and collapsing cores packed into just a few light years, you have to ask, what happens when you go right into the most extreme environment in the Milky Way, close to the central supermassive black hole, where gravity, density, and radiation are all cranked up even higher? How close to a supermassive black hole can stars still form like crazy? And what does that do to everything else in the galaxy? Sagittarius C is where Webb pushes that question hard. This region sits only about 300 light-years from Sagittarius A, the Milky Way's central black hole, in the dense inner zone of the galaxy. It's packed with gas and dust, intense radiation, tangled magnetic fields, and yet, Webb's data show it is also a major factory for new stars. You're not talking about a few scattered baby stars here. Estimates from Webb and supporting observations suggest on the order of hundreds of thousands of stars are present or forming in this field alone, embedded in a complex mix of dark clouds and glowing ionized gas. One particularly dense cloud is so thick that background starlight simply does not get through at infrared wavelengths. It shows up as a dark patch surrounded by a swarm of protostars whose outflows glow strongly in the infrared, surrounded by a wide U-shaped region of ionized hydrogen gas. That cyan-colored ionized gas contains needle-like linear features whose origin astronomers still do not fully understand. So you have this obvious tension. The environment near the galactic center is supposed to be hostile to star formation, with strong tidal forces from the central black hole and a high level of turbulence. Yet Sagittarius C is clearly forming stars anyway. That sets up one of the big open questions Webb is being used to test. Are massive stars actually more common in these extreme central regions than out in the quieter spiral arms where the sun lives? Star formation theory has argued for years about whether the initial mass function, the distribution of stellar masses at birth, is universal, or whether it tilts toward more massive stars in harsh environments. The center of a galaxy is a perfect stress test. The gas is denser, the pressure is higher, the radiation fields are stronger, and the gravitational potential changes rapidly over small distances. If anywhere is going to skew the process toward massive stars, it's here. Webb's view of Sagittarius C gives you for the first time the resolution and sensitivity to actually count young objects in such a region, sort them by brightness and color, and start inferring how many are likely high mass compared to low mass. Why does that matter to you, personally? Because massive stars are the element factories that set up the chemistry of planets and life. When a massive star is born, it burns through its fuel quickly. In its core, hydrogen fuses into helium, then helium into carbon and oxygen, and in the later stages, heavier elements like neon, silicon, and iron. When that star ends its life, usually as a supernova, it blasts those elements into the surrounding gas. Over many generations, that enriched material gets built into new stars, planets, and eventually things like your blood, your bones, and the air you breathe. Oxygen in your lungs, carbon in your cells, iron in your hemoglobin, all of that came out of massive stars. So when Webb shows you a region like Sagittarius C, where an estimated 500,000 stars crowd into a relatively small volume near the galactic center, and many of them are likely to be massive, what you're really seeing is a high-efficiency heavy element factory running close to a supermassive black hole. That directly feeds the central parts of the galaxy with metals, changing how future stars and planets in that region will look compared to the outer disk. The question then becomes, what exactly is Webb resolving in Sagittarius C that previous telescopes could not? In the near-infrared, NIRCam can cut through much of the dust that blocks visible light. Webb's Sagittarius C data reveal a thick web of filamentary structures, narrow threads of gas and dust that crisscross the region. Along those filaments, you see compact, bright knots, dense cores that are very likely collapsing into stars right now. One large infrared dark cloud shows up as a wedge-shaped shadow with a bright reddish clump at its tip, a cluster of protostars whose outflows glow strongly in the infrared, surrounded by a wide U-shaped region of ionized hydrogen gas. That cyan-colored ionized gas contains needle-like linear features whose origin astronomers still do not fully understand. You're seeing, in one frame, multiple phases of the star formation process near a supermassive black hole. There are dense cores on the edge of collapse, protostars still accreting material from their envelopes, bipolar outflows carving channels through the surrounding cloud, and large-scale ionized regions lit up by already formed massive stars. In total, the field contains around 500,000 stars at different stages. That is the closest thing you can get right now to an inventory of how gas turns into stars in the most extreme environment the Milky Way offers. Because Webb can separate individual sources at these wavelengths and depths, you can start concretely asking, how many lower mass protostars are there compared to the massive ones? How clustered are they? How close can they form to strong ionizing sources? And how does the local gas density and turbulence affect those numbers? That's not abstract theory anymore. It's statistics based on actual detections. Now connect this to the early universe story you've been following. Environments near galaxy centers today may strongly resemble the conditions in high redshift galaxies, especially those compact starbursts Webb is seeing at redshifts 10 and beyond. There, the gas is dense, the metallicity is still relatively low, the potential wells are deep, and star formation is intense. The main difference is distance and resolution. At billions of light years away, you can't resolve individual cores and filaments. You just get integrated light from entire galaxies or clumps. Sagittarius C and similar central regions like Sagittarius B2 that Webb is now observing act as local analogs. In Sagittarius B2, for example, you have a massive molecular cloud just a few hundred light years from Sagittarius A, containing only a small fraction of the central gas, but responsible for about half of the star formation in the galactic center. Webb's Anarcam and MIRI images there show hidden young stars and thick dust structures that would have been invisible before. Put that side by side with Sagittarius C, and you get a consistent picture. The central few hundred light years of the Milky Way are not dead zones. They're intense, efficient star factories running under extreme conditions. The same physical rules that you are mapping here, how filaments collapse, how feedback shapes the cloud, how massive stars affect their neighbors, are the rules early galaxies had to follow too, just with more gas and more mergers. Webb's Milky Way data become a kind of Rosetta Stone, letting you decode the messy integrated light from distant starbursts using detailed resolved physics from home. So you've now seen Webb do three things at once. It shows you early galaxies forming faster than expected. It shows you monster stars and aggressive black holes in those systems. And it shows you, in your own galaxy, how dense central environments still manage to turn gas into stars right next to a supermassive black hole. All of that is about making the raw material for planets and life, heavy elements and dust. The next step is obvious. If Webb can track how and where the elements are made, and how efficiently stars form in extreme places, what can it do when you look at the small scale, at actual planets around other stars? Can it use that same infrared power to tell you what alien skies are made of, and whether the chemistry of those worlds makes sense with the violent galactic history you just saw? How far can you really push this telescope if instead of just seeing where planets are, you start reading what their skies are made of, molecule by molecule? That jump started with one very strange world, WSP-39b. This thing is a puffy, hot Saturn, about 700 light-years away. It has roughly the same mass as Saturn, but it's blown up to a much larger radius because it orbits insanely close to its star. 1 year on WSP-39b is about 4 Earth days. Its day-side temperature is around 1600 degrees Fahrenheit, hot enough that clouds can be made of exotic compounds and the atmosphere is extended and fluffy. That puffiness is actually what makes it such a good target. A bigger, hotter atmosphere blocks more starlight when the planet passes in front of its star, so the signal Webb has to measure is stronger. Before Webb, Hubble and Spitzer had already looked at WSP-39b. They saw hints of water vapor and some structure in its spectrum, but the data were limited in wavelength coverage and precision. You could say, yes, there's an atmosphere, and get some broad clues about clouds, but the chemistry was still fuzzy. Webb's job was to hit this same planet with much better tools and see how far you could push atmospheric analysis if you had the right instrument and a bright, easy target. So here's what happened. Using the near-spec instrument in bright object mode, Webb watched WSP-39b as it transited its star, recording how much starlight got through at many different infrared wavelengths. When the data were plotted, there was a small but very clear bump in the transmission spectrum between about 4.1 and 4.6 microns. That subtle rise is exactly what carbon dioxide does in that wavelength range. This was the first unambiguous detection of carbon dioxide in an exoplanet atmosphere. There had been possible hints before, but nothing clean. Webb nailed it in one set of observations. That bump is small, just a fraction of a % change in brightness, but Webb's stability and sensitivity make it stand out with high confidence. You're not squinting at noise, you're seeing a real absorption feature. And because you know exactly how carbon dioxide absorbs light at those wavelengths from lab measurements, you can model how much carbon dioxide there must be in the planet's atmosphere to produce that shape and depth in the spectrum. To see why this works at all, you need to picture what happens during a transit. The planet passes in front of its star and blocks some fraction of the light. But around the solid part of the planet, there's a ring of atmosphere. Starlight grazes through that ring. Different gases in the atmosphere absorb different wavelengths of infrared light. So if you measure the star's brightness very precisely as a function of wavelength while the planet transits, some wavelengths will be blocked a tiny bit more because the atmosphere is more opaque there. Plot those tiny changes versus wavelength, and you get what looks like a barcode with bumps and dips corresponding to water vapor, carbon dioxide, carbon monoxide, maybe methane, and other molecules. That barcode is the transmission spectrum of the atmosphere. Webb's instruments are built exactly for this: high precision, wide wavelength coverage, and extreme stability during long continuous observations. On WASP-39b, Webb measured not just carbon dioxide, but also strong water features, carbon monoxide, and hints of other species, all in one target. This is a big shift from what exoplanet science looked like before. For a lot of early exoplanet atmospheres, you were happy just to say, there's a bump here, probably water, or the spectrum is flatter than expected, maybe clouds. The data were often noisy, with low resolution and narrow wavelength coverage. With Webb and WASP-39b, you get a detailed, multi-feature spectrum that lets you start doing real chemistry and formation modeling. From the shape and strength of the CO2 feature, combined with the water and carbon monoxide signatures, you can estimate the metallicity of the atmosphere, basically how enriched in heavy elements it is compared to the star. For WASP-39b, the results show an enhanced metallicity, higher than the stars, similar to what we see for Saturn and Jupiter in our own solar system, where the giant planets have more heavy elements than the Sun. That's a clue that WASP-39b likely formed farther out in its system, in a region rich in ices and solids, and then migrated inward to its current roasting orbit. You can also use the spectrum to test cloud and haze models. Does the atmosphere look clear with sharp features, or muted with clouds smearing things out? For WASP-39b, Webb data indicate the presence of high-altitude hazes and possibly patchy clouds, but not enough to erase the main molecular features. That helps constrain how aerosols form under extreme temperatures and irradiation, which feeds back into models of hot Jupiter and hot Saturn atmospheres in general. So the key upgrade Webb brings is this: you're no longer asking, does this planet have an atmosphere? You're asking, what's in it, in what amounts, and what does that tell me about where and how this planet formed? That's a different level of question. Now, why care so much about carbon dioxide in particular, if this is just a hot, uninhabitable gas giant? CO2 plays several roles. It's a crucial greenhouse gas that controls climate on rocky planets. It's also a strong absorber in specific infrared bands that are within Webb's sweet spot. If you want to someday detect and measure CO2 on smaller, cooler, Earth-sized planets in habitable zones, you first need a clean demonstration that your telescope and analysis pipeline can actually see that signal in a big, easy target. WASP-39b is that test run. By showing that Webb can pick out the CO2 feature clearly on a hot Saturn, astronomers now know how to plan observations for tougher targets, like temperate super-Earths and mini Neptunes, where the signal will be weaker and the transits might be less frequent. CO2 will be one of the key molecules for future biosignature work. Not because CO2 alone means life, but because its presence, combined with gases like water vapor, methane, and ozone in certain ratios, can point toward interesting, potentially non-equilibrium chemistry. So this is the pivot point. Up to now, you've seen Webb as a machine that rewrites galaxy formation and star formation physics. With WASP-39b, it also becomes a machine that reads alien climate and chemistry, line by line out of light. And once you've proven that you can do high-precision chemistry on a blown-up hot Saturn, the next logical step is to ask, how far can you push this towards smaller, hotter, more extreme rocky worlds, the ones with lava oceans and brutal radiation, where atmospheres are hanging on by a thread? Can Webb still see anything there? And can those worlds tell you if rocky planets can keep their atmospheres at all under extreme conditions? The first rocky planets Webb is really dissecting are not cozy Earth 2.0 worlds, they're hell worlds with surfaces so hot they're probably oceans of lava. And the question is brutal: can an atmosphere survive in that kind of furnace at all? Start with that. Molten rocky worlds with possible atmospheres. One of the headline targets is 55 Cancri e, about 41 light-years away. It's a super-Earth, roughly twice Earth's diameter, several times its mass, and so close to its star that a year lasts about 18 hours. Surface temperatures are thousands of degrees Fahrenheit, hot enough to keep much of the crust in a molten state. Basically, a planet-sized lava ocean. You'd expect any atmosphere to be stripped away or boiled off long ago. Instead, Webb's NIRCam and MIRI data show that the day side of 55 Cancri E is cooler than a bare, dark molten rock would be, and the spectrum is consistent with gases like carbon dioxide or carbon monoxide around the planet. The best explanation right now is a thick, volatile, rich atmosphere, probably fed by gases bubbling out of that magma ocean. It's not comfortable air, but it is an atmosphere on a world that by all rights should have none. And 55 Cancri E is not alone. Webb and other facilities have been running phase curve and eclipse measurements on ultra-hot rocky planets, tracking how their infrared brightness changes over an orbit. On bare rocks with no air, you see huge day-night temperature contrasts. The day side blazing hot, the night side near freezing, with almost no heat transported around the globe. That's what you get for planets like LHS 3844b and GJ 367b, where measurements show sharp thermal contrasts and no evidence for significant heat redistribution. Exactly what you'd expect from airless, tidally locked rocks. But on some targets, the story is different. The brightness pattern is smoother, the day side cooler than a bare rock, and the night side warmer than expected, a sign that something, probably an atmosphere, is moving heat around. That opens the door to the next level. Not just is there air, but can a rocky world this hot keep air for any length of time? That's where the new, strongest evidence yet result comes from, for a molten rocky planet. Recent JWST observations of TOI 561b, an ultra-hot super-Earth that orbits its star in under 11 hours, show exactly that kind of behavior. This planet orbits at a tiny fraction of the Earth-Sun distance, with day-side temperatures above 3,000 Fahrenheit. Yet JWST's near-spec emission spectrum and phase data indicate the day side is cooler than a simple bare rock model predicts, and the pattern fits a thick, volatile, rich atmosphere that's redistributing heat with very fast winds. TOI 561b is being described as a wet lava ball, a world where gases constantly cycle between a molten surface and a dense atmosphere. That's a survival test under the worst possible conditions. If a small rocky planet that close to its star can keep an atmosphere for billions of years, it means rock-atmosphere recycling, gravity, and volatile chemistry can fight back against intense radiation more effectively than many models assumed. It doesn't make TOI 561b habitable, but it proves that small and close to the star does not automatically mean airless. So how does this connect to the question everyone actually cares about, whether Webb can help find another Earth? The answer is, these hell worlds are training targets. If you can pull out atmospheric signals on a planet with a lava ocean, thousands of degrees hotter than Earth, and separate atmospheric effects from bare rock behavior, then doing the same kind of spectroscopy on a cooler, temperate planet is easier from a pure signal-to-noise standpoint. The temperature is lower, but the physics is the same. You watch transits and eclipses, you read the spectrum, you model the climate and composition. Right now, Webb is using these extreme super-Earths to stress test every part of the pipeline: instrument calibration, data reduction, atmospheric retrieval codes, and climate models. You learn how to handle thermal phase curves. You learn what clouds and hazes do at ridiculous temperatures. You learn how surface-atmosphere exchange works when the surface is liquid rock. All of that experience will carry over when you point Webb, or its successors, at cooler planets in habitable zones. But there's a hard limit you need to be honest about. Small rocky planets are simply tough. The best example is the TRAPPIST-1 system, a compact set of 7 Earth-sized planets around a tiny, cool red dwarf star about 40 light-years away. You might expect Webb to just read off their atmospheres like barcodes and settle the habitability question overnight. That hasn't happened. Early JWST transmission spectra for TRAPPIST-1b and C show no sign of thick hydrogen-helium atmospheres. That's not a failure. That's evidence that any light, puffy primordial atmospheres have probably been stripped away by the star's intense radiation and flares, especially this close in. Recent studies argue that TRAPPIST-1c also lacks a dense hydrogen-rich envelope. For some of the outer planets, like TRAPPIST-1e, the latest results hint that a denser, perhaps Titan-like atmosphere might still be possible, but the data are right at the edge of what you can currently pull out, and stellar activity contaminates the signal. That's the honest tension you have to sit with. Webb is powerful, but these signals are small. The planet only blocks a tiny fraction of the star's light, and the atmospheric effect is a tiny fraction of that. The host star itself is noisy, covered in spots and flares that change the light in ways that can mimic or hide atmospheric features. Getting from "there might be an atmosphere" to "here is the exact mix of gases" is a long, hard process, especially for Earth-sized planets. So where does that leave you on the big question? It means Webb is not the "we found life" telescope. It is the "we learned how to read small planet atmospheres properly" telescope. On hell worlds like 55 Cancri E and TOI 561b, it's proving that rocky planets can keep atmospheres in extreme conditions, and that we can detect those atmospheres and constrain their composition. On systems like TRAPPIST-1, it's drawing firm lines about what atmospheres don't exist, ruling out thick hydrogen-helium blankets and pushing models toward thinner secondary atmospheres, if any. That technical groundwork is exactly what future missions will need. If the next generation of space telescopes wants to look for biosignatures, combinations of gases like oxygen, methane, ozone, and CO2 that are hard to explain without biology, you have to rely on methods that Webb is testing right now. You need to know how stellar spots fake signals, how haze flattens spectra, how to interpret phase curves, how to separate bare rocks from true atmospheres. So the real message is this: Webb is not jumping straight to "we found life." It's building the playbook. It's showing that rocky planets can hold on to air even in extreme star-blasted orbits, that some get stripped clean, and that we can tell the difference from thousands of light years away. Once you trust those tools on hell worlds and marginal cases, using them on calmer, temperate planets in the habitable zone becomes the next logical step. And if you can read the skies of hot giants and molten super-Earths, the next natural scale-up is to look at where those planets come from, the disks of dust and gas around young stars, where ice lines, organics, and solid building blocks decide what kinds of planets form in the first place. If you want to know how common Earth-like worlds might really be, you have to see how the raw material is laid out before any planet ever appears. How do you go from raw gas and dust around a young star to actual planets? And how early does that structure start to look like a solar system in progress? That's what Webb is hitting now with protoplanetary disks. Around young stars, you get flat, rotating disks of dust and gas, the places where planets grow. In infrared images and spectra, Webb is resolving those disks with enough detail to see rings, gaps, and even spiral patterns, the same kind of structure that ALMA first hinted at in millimeter light. Webb's mid-infrared data pin down which regions are warm, which are cooler, and what the dust is made of. So you're not just seeing a disk, you're seeing where material is being cleared out, piled up, or heated. So the first question is straightforward. What do these disks actually look like when Webb zooms in? Take edge-on and face-on disks. For face-on disks, Webb's NIRCam and MIRI images show bright central regions with rings and gaps further out. Those gaps can mark places where young planets are carving paths through the disk, or where dust grains are getting trapped by pressure bumps. For edge-on disks like HH30 or IRS 04302, Webb shows a dark lane of dense dust with glowing lobes above and below, and you can measure how thick the dust layer is, how sharply it flares, and how it changes with distance from the star. Combined with spectra, you can tell if grains are still tiny or if they've grown to pebbles and rocks. Once you see the structure, the next key point is temperature, because temperature decides what's solid and what's gas. That's where snowlines come in, and Webb is finally tracking them in detail. A snowline is the distance from the star where a specific volatile, like water, switches from gas to ice. Inside the water snowline, water is vapor. Outside, it freezes onto dust grains as ice. That change matters because icy grains stick together more easily and carry water into forming planets. Webb's MRI spectra of disks show water vapor lines that brighten or fade at different distances, and in some systems, you see excess cool water emission near where the water snowline should be. That's evidence that ice-rich pebbles are drifting inward and releasing water vapor as they cross into warmer zones. In PDS 70, a system with a known giant planet carving a wide gap between inner and outer disk, Webb has now detected water vapor in the inner disk. That tells you that any rocky planets forming close to the star still have access to a water reservoir, despite the large gap outside. The column densities imply the water is being created and shielded in place, and possibly replenished from the outer disk. From a planet formation perspective, that's huge. It means inner rocky planets in some systems can inherit water even after giant planets form and sculpt the outer disk. So you can see where water is gas, where it's ice, and how it moves. The next step is to ask how complex the chemistry gets before planets even exist. Here, Webb has gone from, we see some water and CO2, to these disks are chemical factories. In one low-mass star system, ISO CHAI 147, Webb's MRI spectrum shows the richest hydrocarbon chemistry ever seen in a protoplanetary disk. 13 different carbon-bearing molecules, including ethane, ethylene, propyne, and the methyl radical, all detected for the first time in a disk. In other disks, Webb is picking up signatures of aromatics like benzene, plus CO2, water, and other organics in the regions where rocky planets will form. On top of that, near-spec observations of edge-on disks like HH48NE reveal absorption from major ice components, water ice, CO2 ice, and other species frozen onto dust grains in the cold midplane. Those ices are the raw stock for comets and icy planetesimals. Combined with lab data and models, Webb spectra show that many disks don't start from scratch chemically. They inherit molecules from the cold clouds that form them, and then those molecules get processed, broken, and rebuilt into more complex organics as the disk evolves. So by the time any surface cools into a solid planet, the local environment is already loaded with water, CO2, hydrocarbons, and potentially prebiotic molecules. That means the question shifts from, do you have the ingredients, to how are they distributed and which planets get them? To answer that, you need to tie disk properties to the actual exoplanet populations we see. ALMA has mapped dozens of disks at millimeter wavelengths, measuring dust mass and gas mass, ring structures, and gaps at tens of astronomical units. Webb comes in closer, probing the inner few astronomical units in infrared, where terrestrial planets and hot Jupiters form. Studies now show that disks with large, deep gaps and strong ring patterns are exactly the kind of systems where we go on to find giant planets and mini-Neptunes. Meanwhile, disks with less massive outer regions but active inner chemistry line up better with systems that end up dominated by super-Earths and mini-Neptunes close to the star. That connection explains why our solar system might be the odd one out. The mix of hot Jupiters, mini-Neptunes, and tightly packed super-Earths that Kepler and ground-based surveys see around other stars matches what you'd expect from many of these disks: lots of mass close in, frequent migration, and strong structure in the outer disk. A system with small rocky planets and gas giants parked far out, like ours, may require a more specific disk history or simply be less common. Webb is filling in the before picture that goes with the after exoplanet demographics. None of this comes from Webb alone. The real power is in the combination with ALMA and other radio facilities. Millimeter data from ALMA trace cold dust and molecules in the outer disk, tens of astronomical units out, and measure how much gas is left to form giants. Webb's infrared data show warm dust and gas in the inner disk, within a few astronomical units, where rocky planets and close-in giants grow. When you overlay the two, you get a nearly continuous map, from the hot inner rim out to the cold outer reservoir. Recent joint JWST ALMA work on systems like HH30 and the very young protostar HOPS 315 push this further. HH30 shows that large dust grains have settled into a thin midplane layer, an important step toward forming planetesimals. HOPS 315, even earlier in its evolution, already shows a silicate-rich disk condensing into solid silicates, plus jets and outflows shaping the surrounding gas, literally catching the earliest steps of a new solar system. Together, these datasets take you from tiny dust grains to pebbles, then to planet-building solids and emerging planets. So by zooming out from individual planets to entire disks, Webb is telling you where water, carbon, and organics live before any planet is finished, how those materials move across snowlines, and how disk structure sets the menu of planets a system is likely to build. But that naturally raises the next question. Where do those ices and organics come from in the first place? If disks are already chemically rich, what did they inherit from the dark clouds they formed out of? And how early do water and complex molecules start hitching a ride on dust grains that will eventually turn into comets and oceans? To answer that, you have to go one step earlier than disks, into the cold, dense, almost invisible clouds between the stars, and let Webb look for water and organics frozen onto dust long before any star ever lights up. How early do the ingredients for life show up, if Webb is already seeing water and complex organics not on planets, not even in disks, but frozen onto dust grains in pitch-black clouds before any star has fully formed? Start with those dark clouds. In regions like the Chameleon 1 molecular cloud, a few hundred light-years away, the gas is so cold and dense that it sits only a few dozen degrees above absolute zero. There's almost no visible light. But Webb's infrared spectrographs, NIRSpec and MIRI, can still pick up the faint glow of background stars shining through. In that light, you see absorption features, tiny dips at specific wavelengths, carved out by ices on dust grains along the line of sight. When teams analyzed those spectra, they found a full inventory of frozen molecules: water ice, carbon dioxide ice, carbon monoxide, methane, ammonia, and methanol, all locked in layers on dust grains inside the cloud. This is important because these dense cores in Chameleon 1 are the raw material for future stars and disks. You're not seeing chemistry switch on after a star forms. You're seeing it already running in the dark before starlight. Laboratory work and modeling tied to these data show that reactions on ice surfaces, helped by tiny amounts of heat and UV light, build more complex molecules in these frozen mantles than you'd get in gas alone. That means dust grains entering a disk aren't just rock plus water. They're already carrying a mix of ices and organics inside the cloud. Then, once a protostar actually lights up in the middle of that kind of cloud, Webb sees the next step. In objects like NGC 1333 IRS-2A, very young protostars still buried in thick envelopes, MIRI spectra show strong signatures of water and a pile of other molecules in the warm gas around them. You see water emission lines, OH, and a zoo of other species in both the inner envelope and in shocks from outflows slamming into surrounding gas. Surveys like JWST, which use Webb to look at multiple young protostars, consistently detect water emission near the source and in the highest density shocks. That tells you that water is not arriving late in the game. It's being carried right into the region where disks form, along with the gas and dust collapsing onto the protostar. The material that will become the protoplanetary disk starts out already wet. When that disk later cools and fragments into comets, asteroids, and planets, water has been in the pipeline from the cloud core stage onward. That lines up with the idea that Earth's water likely came from icy bodies formed beyond the snowline and then delivered inward, and Webb is now seeing that behavior in real time in other systems. It doesn't stop at water and simple ices. Some of Webb's most striking results are about complex organics in these early stages. In the same Chameleon 1 cloud, the ice spectra don't just show water, CO2, and methanol. They also hint at more complex prebiotic molecules in the solid phase. In the JWST program, looking at protostars like IRS-2A, Webb has directly identified solid acetaldehyde, ethanol, methyl formate, and likely acetic acid in the ice around the protostar. Exactly the kind of carbon-bearing compounds you expect to feed into more complex chemistry, including amino acids, sugars, and other biologically relevant molecules. That's the key point here. Prebiotic chemistry is not waiting for a planet with oceans and continents. It's already happening in the ices on dust grains inside dark clouds and in the envelopes around protostars. UV light from nearby stars, cosmic rays, and gentle heating all drive reactions in those ices. Lab experiments that mimic these conditions show that when you process these mixtures of water, CO2, ammonia, and organics, you can make amino acids and other complex molecules in the solid phase. Webb's detections are tying those lab results to actual cosmic environments. Now, connect that to the chain of custody for material in a planetary system. You start with the cold molecular cloud, where dust grains collect ices and build up organics. That cloud collapses into a protostar and disk, pulling those ice-coated grains into orbit. In the outer disk, those grains clump into pebbles and then into icy planetesimals and comet-sized bodies. Some of those stay out as Kuiper belt-like objects. Others get scattered inward or collide with growing planets. Each impact delivers water and organics to young worlds. Webb, by surveying clouds, protostars, and disks at different stages, is literally watching that flow from cloud to disk to solid bodies. That picture lines up with what we infer in our own solar system. Isotopic measurements suggest a mix of sources for Earth's water and organics, some from asteroids, some from comets, all originally drawn from icy material beyond the snowline. And Webb is now seeing the same structure and chemistry in other systems, implying that this sequence, cloud to disk to comet to ocean, is not a one-off story. It's a common path. So where does this leave you in terms of the life question? It means that the ingredients for life are not rare. Water ice, CO2, methane, ammonia, and complex organics show up in cold clouds. They survive into protostellar envelopes. They get carried into disks and end up in the building blocks of planets. Webb is basically shouting that the raw stuff of biology, water, and organic chemistry is baked into the standard way stars and planets form. But there's a line you can't cross yet. Having ingredients everywhere does not mean life is everywhere. Going from water and organics to cells, metabolism, and evolution requires a whole stack of conditions that Webb cannot see directly: surface environments, long-term stability, energy flows, and time. What Webb is doing is removing the first excuse. You can't say maybe life is rare because the chemistry is hard to get. The chemistry is clearly not hard to get. It happens in the dark, before planets, as a byproduct of how ice and dust behave in space. So you end up with the sober but very strong conclusion. Life's ingredients are common, scattered across clouds, disks, and forming systems all over the galaxy. Whether those ingredients ever assemble into biology is still an open question, one that will need future telescopes to tackle with direct atmospheric biosignature searches and maybe, one day, surface imaging. And if the small-scale story, water, organics, building blocks, turns out to be easy, then the big question shifts back to the large-scale framework. If the universe is this good at making star-forming clouds, chemically rich disks, and bright early galaxies, are the rules we use for gravity, dark matter, and structure formation really as solid as we think? Or is Webb's early universe data telling you that the cosmic rulebook itself needs edits? How solid is your cosmic rulebook if one telescope keeps finding galaxies that look too big, too bright, and too evolved in a universe that's still just a few 100 million years old? This is where Webb starts pressing on the standard lambda CDM model, the framework with dark energy, cold dark matter, and gravity described by general relativity. That model has done extremely well with the cosmic microwave background and large-scale structure. But when Webb looks at the first few 100 million years, the amount of structure it sees is uncomfortable. Start with the most direct issue: too much structure too soon. When observers count bright, massive galaxy candidates at redshifts above 10, even after more careful follow-up, they still find more luminous objects than many pre-Webb simulations predicted for those early times. Deep surveys like JWST, SEERS, and others report high number densities of UV-bright galaxies at redshifts 8 through 13. In some early analyses, inferred stellar masses for the brightest objects came out as high as 10 to the 10th solar masses within a few 100 million years of the Big Bang. Later work has revised some of those masses downward, but even conservative estimates still leave you with a population of bright galaxies whose abundance strains standard expectations. In lambda CDM, dark matter halos grow hierarchically. Small halos form first, merge, and build larger halos over time. The number of very massive halos at redshifts 10 to 15 is limited by how fast initial density fluctuations can collapse. If you assume normal star formation and standard stellar populations, you translate halo mass into light and get predictions for how many bright galaxies you should see in a given volume. Webb's counts at the bright end seem high compared with those predictions in the first few 100 million years, even after you account for uncertainties. That doesn't immediately kill the model, but it does tell you that at least one part of the halo mass to stars to light chain is off. To figure out which part, you need to measure not just how many galaxies there are, but how much mass is in the halos that host them, and how that compares to their brightness. That's where gravitational lensing becomes a key tool, and Webb's imaging turns lens clusters into dark matter microscopes. In fields like SMACS 0723 and other massive clusters, the combined gravity of the cluster's dark matter and galaxies bends light from more distant background galaxies, turning them into arcs, stretched shapes, and multiple images. By mapping the positions and shapes of those lens galaxies with Webb's sharp resolution, astronomers can reconstruct the cluster's mass distribution, including the dark matter component. This gives you very detailed mass maps on scales of tens to hundreds of thousands of light years. Those reconstructions are important for two reasons. First, they tell you how much dark matter is really there and how it's distributed, letting you test whether halo structures match lambda CDM expectations at intermediate redshifts. Second, lensing boosts the brightness of background high redshift galaxies, letting Webb see fainter objects than it could without the lens. But to interpret those magnified galaxies correctly, you need accurate lens models. That's why high-resolution imaging and spectroscopic redshifts from Webb are critical. They tighten up lens models and reduce uncertainties in magnification, which feeds directly into the inferred intrinsic luminosities and masses of early galaxies. Even in unlensed fields, Webb is now directly probing the mass-luminosity relation at high redshift, and this is where things start to look weird. In simple terms, for a given halo mass, you expect a certain typical brightness from its stars. That mapping is crucial for using galaxy surveys to infer halo populations and test cosmological models. But JWST data from the first billion years show that brightness does not track mass in the same way it does later. In some samples, galaxies at given halo mass appear significantly brighter than expected, implying higher star formation efficiencies or more light per unit stellar mass. If you just take those luminosities at face value, you're forced into galaxies that converted gas into stars very efficiently, up to tens of % of their baryons in stars in a short time. That's not impossible, but it pushes standard feedback models hard. Alternatively, your assumed stellar populations might be wrong. If the early stellar initial mass function is top-heavy, with more massive, luminous stars, you can get more light for less mass. In that case, some of the mismatch between mass and luminosity comes from the stars themselves being different, not from the halos forming too fast. At this point, theorists are splitting their efforts between what you could call astrofixes and more radical new physics ideas. The astrofixes are changes to the baryonic side of the problem. You can make stellar populations more top-heavy. If early stars are on average more massive and hotter, they produce more UV light and ionizing photons per unit mass, matching Webb's bright galaxies in fast reionization without changing dark matter. You can change gas physics. If cooling is more efficient in metal-poor gas, or if dense gas clumps are more stable against feedback in early halos, you can ramp up star formation in compact regions. You can tweak dust. Less dust or different dust properties at high redshift would let more UV light escape, making galaxies appear brighter than models that assume local dust laws. These changes don't require new fundamental physics, just different recipes for how gas, stars, and dust behave in early galaxies. A lot of current work is in this category, updating simulations to match JWST's constraints. On the more radical side, some researchers are exploring whether dark matter halos might form or collapse earlier than standard CDM simulations suggest, perhaps due to changes in the primordial power spectrum, interactions in the dark sector, or alternative dark matter models. Others probe modified gravity scenarios, though these have to thread a very tight needle. They must keep the success of LCDM on large scales and in the cosmic microwave background while allowing more rapid early structure growth. So far, no alternative has gained enough evidence to displace LCDM. But the fact that people are testing them shows how seriously the community takes Webb's early universe results. The honest status right now is this: Webb has not overthrown LCDM. The cosmic microwave background, baryon acoustic oscillations, and large-scale structures still fit the standard model well. Many of the earliest JWST breaks cosmology claims have softened as better redshifts and more careful mass estimates came in. Some of the brightest early candidates turned out to be less extreme once spectra pinned down their distances. But even after the dust settled, there remain real tensions in the mass-luminosity relation, the abundance of bright galaxies at high redshift, and the speed of reionization. So a better way to think about Webb is this: it's the auditor of cosmology. It's not tearing up the financial statements yet, but it is going line by line through the assumptions about how dark matter halos translate into galaxies, how fast those galaxies light up, and how early heavy elements and black holes appear. Every shortcut and every approximation that worked fine when we only had data from redshift 6 and below is now being stress tested against real measurements from redshifts 10, 12, and beyond. For you, that means the story is still in motion. The standard cosmological model is holding up, but only by integrating more extreme star formation, more intense feedback, and possibly different stellar populations in the first few 100 million years. If those astrofixes end up explaining everything, LCDM will come out of this sharper and more constrained. If they don't, and if multiple independent lines of Webb data keep pointing to the same mismatches, then pressure will grow for deeper changes on the dark matter or gravity side. Either way, Webb has changed the tone of the conversation. The early universe is no longer a place you just extrapolate to. It's a data-rich regime where the model has to perform under hard conditions. And that sets up the final turn in this story. If Webb has already reshaped how you think about the first stars, the first galaxies, dark matter, and the basic rulebook of structure formation, what happens as the mission keeps going, stacking deeper fields, targeting more exoplanets, and catching rare transients? How far can it push from first light to the first serious hints of first life before the next generation of telescopes takes over? How do you even judge finished when every time Webb looks deeper, something new breaks your expectations? From here on, the game is about pushing everything it already did much further. The first deep fields and early galaxy surveys were just a start. Over the next years, long-term survey programs will keep stacking exposure time on the same patches of sky, over and over. Every extra hour pulls in fainter galaxies, smaller systems, and pushes the redshift frontier out beyond 14, maybe toward 15 and beyond. That's light coming from less than 250 million years after the Big Bang. With bigger samples, you won't just say, wow, there are early galaxies. You'll be able to measure solid statistics. How many there are at each brightness, how clustered they are, how their sizes and shapes evolve. That turns "this looks weird" into "here's exactly how the early universe was structured, and here's where the models fail numerically." At the same time, the reionization story is going to get much sharper. Right now, you've seen a few standout galaxies, like Jade's GSZ13, carving bubbles in the hydrogen fog. Next, survey teams will go after whole populations, mapping Lyman Alpha and other lines from hundreds or thousands of galaxies across a range of redshifts. The goal is to build a 3D map of how the cosmic fog lifted, which regions cleared first, how big the ionized bubbles were, and how quickly they overlapped. Think of it like a weather map of the young universe, showing pockets of clear sky growing inside a neutral cloud deck. When you line that map up against the distribution of galaxies and their luminosities, you'll get a direct test of whether early galaxies alone could reionize the universe, or whether you need extra sources like faint AGN or exotic stellar populations. On the exoplanets side, Webb is going to keep playing both offense and defense. On offense, it stays focused on easy atmospheric targets: hot Jupiters, warm Neptunes, puffy super-Earths. The planets where big, extended atmospheres and frequent transits give you strong signals. Those systems are where observers will refine every part of the workflow, from instrument stability to retrieval codes, and keep adding molecules to the list. More precise water abundances, CO2, CO, maybe CH4, and other species, plus cloud and haze properties. On defense, it starts taking real shots at smaller, cooler planets that sit in or near their star's habitable zones, especially around M-dwarfs, where the transit signals are larger. You're not jumping straight to "we found life," but you are finally probing for the right kinds of gases on the right kinds of worlds: CO2 and water on temperate super-Earths, hints of methane in the right context, constraints on whether these planets even have substantial atmospheres. Some of those observations will come back empty: thin air, stripped planets, confusing stellar noise. Others will show stable, dense atmospheres where climate modeling actually matters. The point is that Webb is building a small but crucial list of targets where future missions, built specifically to chase biosignatures, will know exactly where to point and what to look for. Then there's the time domain side of the story, the part you can't predict in detail. As Webb revisits deep fields and monitor regions, it will start catching transients, things that change or appear suddenly. That includes supernovae from very early generations of stars brightening and fading at redshifts where we've never seen them before. Each one is a direct probe of how massive stars lived and died in young galaxies, what elements they produced, and how much energy they dumped back into the gas. It also includes other surprises: flares from active black holes, tidal disruption events, maybe odd one-off explosions that don't fit clean categories yet. Every Webb image you see is not just a pretty picture, it's a data bomb under our theories. A deep field means new constraints on dark matter and galaxy formation. A spectrum of a distant galaxy means a new point on the chemical and reionization timeline. A transmission spectrum of an exoplanet means another test of how atmospheres behave and another calibration point for future biosignature hunts. Even the boring targets are sharpening the tools that will eventually be used on the truly high-stakes ones. And the wildest part is, we're still in the early chapters of this mission. Webb's mirror is healthy, its instruments are performing above spec, and long-term survey programs are just getting going. As more data pile up, the noise will drop, rare objects will become common samples, and small tensions will either be resolved or solidified into real cracks that demand new physics. On the exoplanet side, each new atmosphere Webb measures makes the next one easier to interpret, and pushes closer to the day when someone can say, with evidence, that a rocky planet's sky does not look like pure chemistry alone can explain. So you're not just watching a telescope do its job, you're watching the universe being forced to answer questions it's never had to answer before. The models have to match the data now, not the other way around. And from first light to the first serious hints of life-friendly atmospheres, Webb is the bridge. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.